Hello, we are doing lecture number 9 this afternoon, which, as you will see, encompasses the study of struts or compression members. When we talk about struts and compression members, we're talking about columns in the common jargon. Columns are the things that hold floors up between multi-story buildings and hold buildings up. So they're very important parts of the fabric of a structure. Now, you all have these notes. Struts are compression members. There can be reversal of stresses where a strut becomes a tension member, but essentially in this course we're going to concentrate on their use as a compression member. These are the symbols that we'll be using. I've got the strut theory as proposed by Leonhard Euler, a very famous Swiss mathematician who lived between 1707 and 1783, who came up with a mathematically correct view of the behavior of struts, but this was his pure mathematical view could only be possible under laboratory conditions, not in the real world. His theory still plays a large part in the analysis of struts. I have the proof here of Euler's proof. d2y dx squared over m over ei is the general differential equation for deflection. And we will be getting onto that later, where you divide the area of the moment diagram by the elastic modulus multiplied by the moment of inertia of the element. I'm not going to go through his theory. For those students who wish to study Euler's theory, please be my guest and go through it. I know that the majority of you want to be able to do the problems to enable you to pass the examination, and so that's what I will focus on. Incidentally, this table 4632 appears in both codes, AS 3600 and AS 4100, and what it talks about is the end fixity for a column. If I use this ruler to illustrate end fixity conditions as shown in table 4632, a braced member with a pinned end under load would react like that. My fingers are pinned there, there's no fixity. But if you gripped the end there and you loaded it, you would get this sort of shape, which you see in this diagram over there. So moving on, we will ignore sway members at the moment. But we will be using these effective length factors. What the fixity at both ends does, it shortens the effective length of the strut. We multiply the length by a factor of 0.7. Where you have a pinned joint at one end and a fixed at the other end, we use a factor of 0.85. And where it's pinned at both ends, we use a factor of 1, so we use the full length of the strut. But that will become more obvious to you as we move on. This is the mathematics that some of you might want to go through, but I'm not going to do that because I know a lot of students don't actually do the second semester mathematics. So we'll go straight on to worked examples. Example, what is the Euler buckling load for a steel rod 4 meters long, 30 millimeters in diameter, so it's round, pinned at both ends? The elastic modulus being 200 kilonewtons per square millimeter. Now, for what I showed you in 4632, if it is pinned at both ends, we will use the full effective length, and here I have it. L equals L for pinned ends, which equals 4 meters. Now, the moment of inertia for a circular object is pi d to the 4th over 64. that is for a solid circular object, not for a hollow circular object. So the moment of inertia then pi d to the 4th over 64, which in this particular case we have pi multiplied by the diameter of the bar, which is 30 millimeters, power of 4 divided by 64, which gives you a final moment of inertia of 39,765 millimeters to the power of 4. Plugging the moment of inertia, etc., into the Euler formula to find P, which is the force, we have pi squared times EI divided by KL squared, all squared, KL all squared. So this is the basic Euler formula for a strut. So pi squared multiplied by E, which is 200 times 10 cubed. That's 200 kilonewtons per square millimeter, or 200,000 newtons per square millimeter, multiplied by the moment of inertia, which we computed up there, divided by the actual effective length from the previous table, which is 1, because the strut is pinned at both ends. 1 times the length, which is 4 meters, 1 times 4,000, all squared. And when you solve that, when you do that arithmetic, you'll find that the Euler buckling load is 4.907 kilonewtons. There is some more technical data down there regarding the Euler buckling stress plotted against the slenderness ratio. This is hyperbolic, i.e. y equals a over x squared, as the length over the radius of gyration decreases. And you can see this there. This is the Euler curve plotted on the x and y axis. It's a theoretical curve. It is not realistic. These curves from later researchers are far more realistic as to the behavior of struts. Note at the bottom here, note the safe working stress for the strut is obtained by dividing the buckling stress by a factor of safety. Tests and struts indicate that buckling takes place at lower stresses than those obtained from Euler. Due to the fact that various researchers have come up with modifications to Euler's theory, namely Rankine, Perry-Robertson and others, the latest Australian codes illustrate present-day philosophy on struts. So as we said at the outset, Euler's theory was purely theoretical and does not reflect reality. This graph shows the results of various researchers. Johnson was one, Rankine, Perry-Robertson, etc. Their graph isn't on there, but it would probably follow this one pretty closely. And Euler's there is hyperbolic, so we will ignore Euler. It's sort of correct down in the lower regions, and then he just keeps going because that's the pure mathematics of the thing, which isn't reality. So that's a graph for mild steel struts with pinned ends. Now we look at Rankine-Gordon. For a pin-ended strut where the length equals the length, the actual length, and F equals the failure stress, Rankine-Gordon came up with this formula. The stress equals the stress and compression divided by 1 plus the stress and compression divided by pi squared E L over R all squared. We can replace the stress over pi squared E by a constant A, which you can see down in this table over here. This is a constant A, a timber strut with pinned ends, with fixed ends. When I say pinned ends, we're looking at this situation. When we're talking about fixed ends, we're talking about this situation as you saw in that earlier table. A strut denoted like that shows you that the ends are fixed. With pins at the end, it's free to buckle in an arc-like shape. So we replace the FC over pi squared E by A, and this constant allows for material imperfections and end fixity conditions. P, the allowable load, is then given by this formula once we've replaced the component in there. And the following table can then be used for timber and mild steel. There are far more constants that can be used, but in our course this is all we're going to be looking at. So the FC that we've chosen for timber is 35 NPa, or newtons per square millimeter, and the FC for mild steel 320 newtons per square millimeter. And of course they have different factors for pinned ends and fixed ends in the steel as for the timber. A factor of safety is used by reducing FC to obtain a working stress. Example, a 50 by 50 by 6 equal angle is used as a strut in a roof truss. Now, if I could just sketch that for you, because some of you might not know what it is, but you should know. An equal angle looks like this. It is a hot rolled section, comes out the steel mill, some BHP or one steel, and that is an equal angle. Now if we said a 50 by 50 by 6, that dimension is 50 millimeters, this dimension is 50 millimeters, and the thickness is 6 millimeters. That is a 50 by 50 by 6 EA for equal angle. And it's used as a strut in a roof truss. So if you can think of a roof truss that might look like this. A compression member in this roof truss, a strut, compression member, it uses an equal angle to fabricate this roof truss, which carries roof sheeting and hence covers a building. So calculate using A, Euler, and B, Rankine-Gordon, the safe axial loads. The Young's modulus of elasticity, or the elastic modulus for steel, we're using the 200 by 10 cubed newtons per square millimeter. The moment of inertia for a 50 by 50 by 6 equal angle is 0.0536 by 10 to the 6 newtons per millimeter to the fourth. Sorry, that's not newtons, just millimeters to the fourth. That's incorrect. So just change your notes there, please, because the newtons don't come into moments of inertia. Now, just as a matter of interest, the IY is the weakest axis for an equal angle, and that runs through there. It's not one of the rectangular axes, and it's not the axis that runs through there. It's the x-axis on an equal angle. This is the YY axis. And when you're choosing equal angles, and from steel tables, always use the YY axis. It gives you the least moment of inertia. You could check that up by looking at the tables. At the same time, you need to look up the radius of gyration about the YY axis, which you will find from your one steel tables, which will also give you the area, the cross-sectional area of the whole angle. Now, the Rankine constant for pinned ends and mild steel is 1 over 7,500. And if you go back to your notes there you will see it. Pinned ends, mild steel, 1 over 7,500. We're going to use a safety factor of 2, So the solution by Euler, Euler's formula for the load is pi squared EI over KL squared, K being the factor for end fixity. In this case, being pinned both ends, it is 1. So plug your numbers into your formula, pi squared multiplied by the elastic modulus multiplied by the moment of inertia, and divided by the factor for the end fixity multiplied by the actual length of the strut, all squared. Gives you a load of 11.76 kilonewtons, but we're actually applying a factor of safety of 2. So we have to divide that by 2, and we end up with a safe load of 5.88 kilonewtons, which is half of this. The actual load divided by 2. So that's part A of the solution. Part B, using Rankine-Gordon, we apply the formula that we discussed on the previous page. The FC given to you for the steel is 320 newtons per square millimeter. The area of the angle is 568 millimeters squared. Unity plus little a, which is 1/7,500. We had a look at that earlier on the table. Divided by the length, divided by the least radius of gyration, Ry, all squared. The whole thing multiplied by 10 to the minus 3 to bring it to kilonewtons. Otherwise, your answer would come out in newtons. And we get a load of 13.27 kilonewtons. If we apply the safety factor of 2, which we're obliged to in this case, we get a safe load of 6.63 kilonewtons. This brings us to the end of the worked examples and the notes on Euler and struts. And so what we will do now is go on to the exercises in the tutorial. You all have these questions over there. I will repeat the questions as I go through each tutorial question. We will refer back to these. So that ends the lecture. Thank you.